So this first condition, h is equal to 0 at x equal to 0, it gives us that a should be 0. That means h should be equal to hx should be equal to b sine kx. Okay. Then from the second condition, when you put x equal to a, h is equal to 0. So when you put x equal to a, we should get h is equal to 0. That means b sine ka is equal to 0. So we have from the second condition, b sine ka is equal to 0. Now we have two terms, b and sine ka. Their multiplication is 0. But we cannot take b equal to 0, because otherwise, if b is equal to 0, then both a and b are 0. That means h is always 0. And h is always 0 means f is 0. F is 0 means u is 0. That means the membrane is not vibrating. So b cannot be 0. That means sine ka should be 0. Okay. So that implies, this implies sine ka is equal to 0. This further implies ka equal to n pi, where n goes from 1 to 3 and so on. Let us call it m pi, where m goes from 1, 2, 3, 4 and so on. Okay. This implies k equal to m pi by a. K equal to m pi by a, where m goes from 1, m goes from 1, 2, 3 and so on. Okay, this is fine. Next, let us also solve for q. So we have not written any equation number so far. Okay. This is fine. So in precisely the same fashion, we can conclude that for the solution Q, we conclude that for the solution Q, C should be 0 and P must be restricted to values n pi by b, where n is an integer. So similarly, so in precisely the same fashion, we conclude that C should be 0 and P must be restricted to the values P equal to n pi by b, where n is integer 1, 2, 3 and so on. Okay. P is given by this. So we thus obtain the solutions h equal to hm, because for each value of m we get a different value of k, and for each value of k we get different values of h. hm and q equal to qn, where hm x is given by sine m pi by ax and q and y is given by sine n pi by b times y. Here m can take value 1, 2 and so on, and n can take values 1, 2 and so on. As in the case of the vibrating string, it is not necessary to consider negative values of m and n, because the corresponding solutions are essentially the same solutions, except that this will be negative. Hence, the functions Hence the functions f m n x y. This is equal to h m x q n y. This is equal to sine product of these two, sine m pi by ax sine multiplied by sine n pi by b y, where m goes from 1 to 3 and so on, n goes from 1 to 3 and so on. We call this equation number 8. Hence, these functions are the solutions of the Helmholtz equation. Helmholtz equation given by equation number 5 that are 0 on the boundary. On the boundary of our membrane. So this equation number 8 is the solution of the Helmholtz equation that satisfy the boundary conditions. Okay. And okay, let me write it on a new sheet of paper. Let us discuss the eigenfunctions and eigenvalues. Eigenfunctions and eigenvalues. Okay, so we have taken care of equation number 5. That is the Helmholtz equation. That is the space-dependent part. Now we turn to equation number 4. That is the time-dependent part. This is equation number 4. Okay, so we have found the solutions for this equation number 5 that satisfy the boundary condition. Now let us solve equation number 4. And from earlier case, we know that since p square equal to nu square minus k square. Okay, this was in equation number 7. In equation number 7, we saw that p square equal to nu square minus k square. Oh. And in equation number 4, we saw that lambda equal to c nu. Right? So since p is in equation 7 and lambda equal to c times nu, in equation number 4, we have lambda equal to c times root over k square plus p square. Hence, to k equal to m pi by a and p equal to n pi by b, there corresponds the value of lambda given by lambda equal to, now it will depend upon two parameters m and n. So lambda m n is given by, I can take this pi outside, so c times pi root over m square by a square plus n square by b square, where m goes from 1 to 3 and so on, n goes from 1 to 3 and so on. We call this equation number 9. Okay. in the ordinary differential equation number 9. Sorry, number 4, not number 9, 4. So what is equation number 4? Equation number 4 is the equation for time dependent part G. So in this G, this lambda, this constant lambda is given by equation number 9. And the solution of this equation is also simple. So a corresponding general solution of equation 4 is given by Gmn of t. This is equal to Vmn cos lambda mn t plus Bmn star sine of lambda mn t. Okay. Here we have introduced the subscript mn because lambda depends upon m and n through equation number 9. Fine. So if I substitute, let me increase this brightness a little bit. Okay. So if I substitute G equal to this in the expression for U, we get, so it follows that the function U m n x y t, this is equal to f m n x y times G m n t, written out as U m n x y t, this is equal to B m n cos lambda m n t, sorry, there is no bracket here, plus B star m n sine lambda m n t multiplied by the space dependent part sine m pi by ax sine n pi by by. This we call equation number 10. So it follows that this function with lambda mn given by equation number 9. So with lambda mn according to equation 9 are solutions of the wave equation 1 that satisfy the boundary conditions number 2, that is that are 0 on the boundary of the rectangular membrane. These functions are called the eigenfunctions. Eigenfunctions or characteristic functions, and the numbers lambda mn, and the numbers lambda mn are called the eigenvalues. or characteristic values. Characteristic values of the vibrating membrane. Of the vibrating membrane. Okay. The frequency of this vibration is given by the frequency of UMN is given by lambda mn divided by twice pi. Here, cos lambda mnt, this is like cos omega t. And omega, we know that omega is twice pi times the frequency. So if you want to find the frequency, you divide omega by twice pi. And here lambda serves the function of omega. So here the frequency of oscillation is lambda mn by twice pi. For different values of m and n, we can get different values of the frequency of oscillation of the rectangular membrane. Okay. Here, it's very interesting that depending on A and B, several functions f of fmn may correspond to the same eigenvalue. So this eigenvalue lambda mn, I repeat, depending on A and B, several functions fmn may correspond to the same eigenvalue. And physically, this means that there may exist vibrations having the same frequency, but entirely different nodal lines. In vibrating string, we say knots. Here we say nodal lines. Okay. And what are these nodal lines? Nodal lines are curves of points on the membrane that do not move. So, so far, this is the eigenfunction of the given problem that satisfy the boundary conditions. Okay, that satisfy the boundary conditions. Now let us look at let me take a new sheet of paper. Now let us find solutions that satisfy the initial conditions. Okay, let us look at solutions that satisfy the initial conditions. So let me move to step number 3. Solution of the model. So solution of the model, that is equation 1, that is a wave equation satisfying the boundary condition given by equation 2 and satisfying the initial condition 3. I think it's already very late, 10:42. Okay, let me continue step number 3 tomorrow. So we shall end here for today. Let me stop the